So my name is Pablo, and I'm here representing Team Cape. And I'm going to be showing you our solution on this final challenge of WDL. Okay, I will go through 3 different stages. So the first part of the presentation is going to be talking about the data and the issues that we found with the data. Second is going to be our model and the approach that we followed. And finally, we'll briefly talk about the SDGs and how this project can have an impact on the sustainability and development goals. Okay. So, what you're about to see on screen is first of all, like a brief mention of the data. And basically, what's important here is that we had 7 data sets. We had information about bats in Bristol. We had information about streetlights, green corridors, etc. So our focus is going to be in the bats, and then we will use all the other information as aggregate data. But this comes with a lot of issues as well, so we will talk about that. So first of all, you see this graph. This is just to portray the differences, like the different types of bats. You can see there's a first species, which is the pipistrellus, I believe, that is really represented in the graph. But as you go on, some species are barely represented in it. Okay, so keep this in mind. Second, what you're about to see is actually the distribution over the years of these bats. So as you can see, the data set goes from, I believe, 1923 to 2020. But there is a clear imbalance in the time frames in which this data points were extracted. And this is actually a big problem, because we also notice that only the year is consistent, and we can't really trust the data at the granularity level of days or even months. So we're limited to looking at years, and even this was not that ideal. Okay, so here what we wanted to show you is the map of what Bristol looks like with the bats. As you can see, we use 3 different colors just to show you. Each color represents one of the most common species within Bristol. And as you can see, there are some species that might prefer green areas, some species that are more within urban areas, and the whole distribution is really sparse. Okay, this graph, or what you're about to see, contains a lot of information, but let's first focus on the bottom side. So we just mentioned that there's a really big problem with the years, and 2013 was the year with the most amount of bats. But if we only look at the granular information, which already reduces the amount of information we have by a lot, you can see the bottom frame of the image. That's 2013, and the red dots are the dates in which the information about bats was collected. So as you can see, most of the information about bats was extracted in 2 dates, making this really inconsistent and unreliable when building a model over findings that have been taken in 2 specific dates. You see a little heat map on the top of the whole population of bats there, and I think the rest of the information we can skip. Yes. So now we wanted to see how this correlates with the other data sets. So we looked at the overlap between the bats, and we also looked at with the different data sets. So for example, on the left side, all of the red dots are the bats, but there's a little tiny blue dot on the bottom right, and that's actually the dark corridor. So it has barely no overlap with the bats, and it's really hard to use this information. The wildlife corridors are more correlated in this sense, just looking at the overlap. And then we also have other data sets like the green areas or the green area species, which have a higher overlap in total. Okay. And finally, what we looked is at the information about moths. This is also this has the biggest overlap with the bats. But again, we have an issue, and that is that the moths in 2013, as an example, the information was only extracted over 2 months. So we can't really extend this to the whole year when it comes to seeing how the bats feed, because the information is really constrained to a specific time of the year. Okay. Also, something we also looked at is there was a question that was proposed, which is which areas are more illuminated, whether urban areas or commercial areas. And we took a subset of the streetlight information, and we figured out that the commercial areas, although less present in there are less commercial areas than urban areas, but they're more illuminated. Okay? So with all of this information, we started our brainstorming, trying to figure out how we can model all of this. But we realized that in order to make a complex model, we would have to take a lot of assumptions. And this is also something that is really hard to sample or to test in real life, because you need people in the field actually switching lights or testing the different solutions that you come up with. So what we ended up doing is we just did an approach or like a method that can be applied not only to bats, but also to other species. And you can actually, it's really, really simple. We simplified it, and you can actually follow this methodology. And you can actually create environments in which you can test whether this works out. And it's similar to what the team before us did, but you will see right now. So first of all, this is the whole population of bats. We take all of the bats as the same, because the data is so scarce that we just decided to do it like this. And for the sake of the presentation, we cluster the information. This is not necessary, as by creating clusters, you're actually displacing the real locations of the bats, but it is way easier to understand. So on the left, you have all of the bats. On the right, you see clusters. And we went one step further and just created 5 clusters so we can show the positioning. So the first step, again, we try to do it as simple as possible and as reusable and scalable as possible. We just create our 5 dots. Each dot represents the bats. Then we create what is called a fully connected graph, which is simply connecting the nodes with each other. And the next step is actually the key part, which is the way we weight these edges. So the way we weight it is completely ad hoc, and you can, it depends on the problem that you're looking at. So you could use the lights, you could use the distances, you could choose the number of green areas in between, the area of the green areas, etc. And the idea is that the solution is really simple, so you can just plug in whatever information you have in whichever numerical format that you need, and you can create the weight that you desire, and then you can test this as much as you can. And finally, what we do is once we have this graph, we compute what is called the minimum spanning tree. And the minimum spanning tree, the idea behind it is that you minimize the cost of this connections between nodes, and you find the minimum expression of this graph. The idea is finding an optimal distribution of paths that can be extracted from this complete graph. We take the assumption, in this case, that the red lines, the paths, are actually the dark corridors. And the idea is that you can simulate as many scenarios as you wish, and you can actually test the different configurations of the graph with this. Okay? Another example here would be using the light information. So what we did here is between 2 nodes, between 2 positions of the bats, there is a paper that talks about the distance, the light distance at which bats are affected by the light. So we took all of the lights that are within that range, I believe it's 50 meters, and we compute the line, and then we can actually use as a weight the number of lights that actually have an impact on that distance. As well, you could use other metrics, but this we found that was really interesting to look at. And this now creates a new graph that can be recomputed into a new distribution. And finally, 2 more interesting points. Here we've been talking about modifying the weights of the edges, but something we tested as well is creating new nodes. So there's a paper that talks about the city of Bath, which is relatively close to Bristol. And the city of Bath they found out that bats really enjoy going through the river, for example. So even if we don't have information of bats on the river, we said what would happen, for example, like we can create fake nodes among the river, and then we can see how the new graph is recomputed. And this is what you can briefly see on the right side. This is just the same test graph, and we created this fake corridor for the bats to use, and then we see how the minimum spanning tree is computed. Okay? And another thing that we also looked at is what happens if we want certain areas to not be crossed by bats. So we also have a snippet of the algorithm where we look at a radius within an area, and all the nodes or all the edges that go through that area, we remove it from the solution. So our solution is based on a minimum spanning tree, but it doesn't have to end up being fully connected. Like all the nodes don't have to be connected within each other. You can have a disconnected graph at the end. Okay, and finally, how does this impact the SDGs, which is some parameter made by the UN. So as you can see, we have SDG 3 that also takes care about the health of animals. We have SDG 7 and 12 in the reduction of energy consumption through the creation of dark corridors. We have SDG 11 on sustainable cities. And finally, we have SDG 15 protecting biodiversity and natural habitats. So yep, question us as much as you wish. And yeah, thank you very much for your time.
Whoever wants to start, go ahead. It's already on, yeah.
It's on. Okay, thank you for the presentation. So I have a sort of couple of technical questions.
Go for it.
And I'll leave the more high-level questions for the others. So actually, other groups use this solution. So what is the motivation? How do you justify the use of the minimum spanning tree? So that forces the corridors to have to be like tree-like structures, which forces the bat to fly somehow around.
First of all, we looked. There's a paper talking about actually the distance covered by bats and also the angle in which they move. So creating direct lines seems like a good approach in that sense. Second, it's true that we're limiting to a minimum spanning tree, but at the same time, we also have code removing certain areas. So you can actually create fake nodes and then remove them, hence removing the tree-like structure when it comes to the minimum spanning tree. We use the minimum spanning tree basically because it was like a really intuitive cost function. So basically, like you remove edges that have high weights, and you just try to minimize that. And that also, like, it's useful towards extracting maybe certain metrics because people understand it. No, it's really explainable.
Okay, I have other questions, but
go ahead. Yeah, let's go.
Okay, so I have the same question I had for the previous team, which is when you define the cost function, is it a static cost function, or do you take into account time of day, if it's middle of the night or early evening?
So I think this is something that I showed at the beginning, that the quality of the data is quite restrictive when it comes to this. So I mentioned the time of the data. The issue as well is that it's not reliable. So some data points say, let's say 5th of June, others say from June to March, or from 1995 to 1998. So there's no way of putting that information into a time series format. Of course, we would like to do that. Also, we realize that maybe the information is also completely biased, because how are these data points extracted? Like, are you just putting bat radars in specific points? What happens with the whole population of bats? Like, we're just plotting bats in specific locations because their radars are there. There could be bats everywhere else. And finally, we decided against making assumptions. Because again, we are not topic experts, and we could create something more complex on top of it, but I think it's better not to do this, because it might look good in the presentation, but what's the real value we're bringing to this? I think it's up to the scientists to actually decide how they can model this, and we're just providing, as I said, a really simple approach that is really easy to understand, and they can play with it as much as they want. So, I mean, I wish we had more time series data, but we just do not. And the cost function, we played, for example, with the number of lights. We also played with the green areas in the zone, and also we created like little metrics around this, like lights per square kilometer, or like the density of light in relationship with the green areas, etc. That's why in some of the plots you see that all of, like, just for testing purposes, all of the edges go towards the left. That's because that's a really green area, and we're just playing with different.
Okay, thank you.
Thanks once more for your presentation. Fantastic. Well, I have a couple of questions. The first one, regarding the cost function, I didn't hear, but I'm sorry if you mentioned variables as criminality or areas that you cannot dim lights. Did you use them in your algorithm? So
one thing that we did use is there's a library called OSMNX, where you can extract geographical like really context-based information. So we didn't look, for example, at criminality rates, but there's other information like schools in the area, for example, which might seem irrelevant, but you can also use this information to model it. So we didn't use criminal data, but we did look at other variables that we do not display here. But,
okay. So based on your assumptions and what you said, and obviously the data is not accurate, what will be the steps that you propose if you're selling this to someone? That will be the next steps to make this a product that could be actually be used. So what kind of data do you need? What kind of data periodicity do you need? What kind of help do you need in the effort to make this a product?
I think to actually package this or like to build it into a fully functional product, the most important part is first interacting with project experts or with domain experts directly, because we like just by creating this, we're already making some assumptions. And those assumptions need scientific background and need people that can actually validate those. I think the most important part is having unbiased data. So first of all, having consistent data, like you can just distribute, I know it's expensive maybe for the city of Bristol, but distribute bat radars all over the place and then see where the bats actually are. Because now we're just assuming that they're in the locations where maybe it's just arbitrary and people, because some of the information was sites, like someone saw a bat there and that's recorded. So that's quite inconsistent. And the most important thing is, again, time is a really important factor. The paper in Bath mentions that there are 2 periods in which bats are not active during the year. So it's like it oscillates. This is something we couldn't verify because we don't have the information to say, hey, when is this happening? So data would be the most important part in this context. Data and the validity of the experts that can give us more insights into it. Because if we have information on when the bats have certain behaviors, then you can actually create more dynamic scenarios in which you can choose how they move within these nodes or create more nodes, or maybe in a season of the year, the city center of Bristol is really packed with people and you want to avoid bats going through that area. So you can create specific solutions.
Thank you so much. Gracias.
Thanks for the presentation. I have a question regarding the final product maybe, because really like the methodology was super well explained, congratulations. But I'm not sure to completely understand like your final solution. So it's a data visualization product where, for example, the Bristol lighting management will be able to have, I don't know, some scenario, some recommendations. Like I saw that you have like a kind of corridors. Is it going to appear as it appeared in your map, like, you know, straight lines, or is it more?
Okay, so I think that the value that we have is that we create some sort of toolbox that they can play with. And the number of nodes you can modify as well to create like these scenarios to adapt it more. The idea of just simply showing it in a graph is that it's quite intuitive. So the visual component in the end would be showing the distribution of these corridors, and then you can actually make accurate decisions with that graph. So for example, you can minimize the number of lights, and then you see, okay, these are the corridors that have the minimum illumination. But what happens if we maximize it, for example? What happens if we look at the connection between bat areas that contain the most amount of light? Maybe that's where you need to change things, and you want to reduce the light there because it will have a lesser impact in the population as these areas are already well illuminated, and by dimming the lights a little bit, you're actually helping the bats. So I think the final visual would be some sort of graph, and then obviously you can extract information from there. So you can have parameters like number of, like amount of light saved, for example. If you're looking at minimizing that, you could see, okay, if we reduce this amount of lights in areas that contain a more than a certain amount of lights, how much energy are we saving by that? And that could just be an output that they see. They see the graph, they see the links, and then they see parameters that they can interpret more accurately.
But concretely, does it mean that from the center management, you will have like the corridor as a straight line, and then you have an additional work, which is to find the spot that you have to light off? Or is it, or in your solution, do you directly propose, okay, so this is the streets that are related to the corridor and that we will need, for example, to light off?
So we're basing the whole solution on these straight lights, but we're also extracting information from the terrain itself. So even if the graph is straight, obviously the distribution of the streets is not straight. Also, an advantage that we saw about this is that we're thinking from a human perspective in the sense of we're looking at streets, but maybe just by dimming 1 or 2 lights in the street, because there's a corridor that goes on top of the houses through that street, you're actually solving the problem. You know, so creating straight lines over the buildings also seemed like a reasonable strategy, because you can specifically target specific like light points that might not have an impact on the whole security of the road, and you're still creating a corridor, because a corridor is not going to be limited to what a human would consider to be a corridor. But yes, obviously we're using straight lines, but again, if you put more nodes in the graph, which you can create, you can work around. So yeah, obviously it's a straight line. And then how do you decide where to put those nodes? So you can cluster in different ways, or you can just use nodes from other distributions. So you could add nodes, for example, on positions where there are moths. And then you can include this in the graph and then create a new tree based on that.
I think my point wasn't about the nodes, or that's perfectly clear, but this is what you said basically, how you take into consideration human perspective, because I have the impression that in your map, you took into consideration bats' perspective, that are, that when they fly, they can do it straight. But as you said, a city is much more complicated. You have a network of streets that is never linear. And so that's what I was trying to understand, how you add this additional layer, and if you would like to add it, or if you already added it in your solution.
Pablo, sorry.
You see what I mean?
Yeah, I think that the problem here is that we showed that the visualization, just for a visualization purpose, only 5 nodes. But of course, we have many points. So we now see the straight lines, but then the final solution won't be a straight line, because we will consider more nodes. So more clusters of bats.
And in order to take into account human variables, you can always change the weight of this axis. So the same way we're computing lights, we focused on lights and green areas because we deemed that to be most important. When it comes to security, you can, for example, count the number of intersections, because there's also those areas seem to have a specific importance when it comes to bats. So you can quantify that. You can quantify. We also looked at sound information. So are bats influenced by sound? There's a paper that says that, for example, the rain actually makes bats hide, but traffic doesn't really have that much of an impact. So those are also variables that are very human-like, and that you can add as a cost within the weights of these graphs, and then you can play with it as much as you want. You can maximize it or minimize it. You can find a path that has, or even population density. You can look at the population density in a specific stretch, and then you can see how many people you're going to be impacted by dimming the lights in that specific stretch.
Okay, thank you.
Thank you for your presentation. So thinking about this in terms of how we would be able to use it with our central management system, can the output of this actually identify the individual street lights that we would want to be making a change to?
So for example, may I go back? Give me a second. In this case, for example, one of the weight functions is the amount of lights that are within a stretch between 2 nodes. By calculating this, you can see that this is an uneven distribution. So there are areas that have a lot of lights, and there are areas that have barely no lights. So we could actually target specific areas that have a high density, and then actually switch specific lights off. So the thing is that this is just a tool that you can use to simulate scenarios. Then you need to have people actually taking, you can be really creative with this. That is my point. For example, you could even look at the type of lights that you have, because maybe it's worth it to switch off specific types of lights, because they are less eco-friendly than others. And then you can prioritize those and give those type of lights So instead of having the number of lights between two nodes, you could have, for example, the types of lights, and then you quantify lights that are worse for the environment in a different way to the way you quantify lights that are better. And then you can pinpoint specific locations and just say, if we remove this light, the whole consistency of the network is still, like people are not that affected in terms of light per square meter, for example, and yet you're removing, you're helping to create this whole corridor.
Thank you.
Maybe I can get one really quick last question. And please try to make it brief since almost running out of time. So compliments, I like the overlapping of the wildlife corridors and the other maps. Which species do you mean in the map green area species? Is it bats or is it something much broader? Because more animals could profit from dark corridors.
So something that we wanted to look at is how all of these data sets correlate. The green area species are actually, I believe we also have even plants in there. So we have a wildlife data set which contains like animal species, but this green area species are basically, we have types of flowers, types of plants, types of trees, etc.
Okay.
So we also looked into that.
Perfect. Thank you very much. Our time is up. A big round of applause, please.
Thank you.